Hi, everyone. Thanks for joining this virtual talk. I'm excited to talk to you today. I'm going to be talking to you about what I call the science of nudging an ecosystem. And to explain what I mean by this, I want to start with a hypothetical. So suppose that you, hypothetically, work on a major web browser security team. And tomorrow, an academic researcher drops a major protocol level vulnerability in TLS 1.2. Now, maybe you don't really work on a browser security team, and so this kind of scenario may not be familiar. And if that's the case, I'll tell you that TLS 1.2 is currently the most common version of TLS deployed on the web, and its successor version, 1.3, is widely used, but not by any means universally supported by servers yet. So our hypothetical scenario is, suppose you get wind of this major vulnerability in TLS 1.2 tomorrow, and you find out that the protocol itself is fundamentally insecure. Your task in this imaginary scenario is to get as many servers as possible to migrate to TLS 1.3, and then eventually, but as quickly as possible, you want to remove TLS 1.2 support from the browser. So for my question for you is, how would you go about doing this? And as you start to think about this, there might be some possible strategies that might come to mind. You might think about maybe broader targeted outreach to website owners, maybe something like collecting contact information from domain registrations or writing developer-focused content or pitching the tech press. You might think about coordinating with other web browsers or getting hosting providers or CDNs to contact their customers. Or you might think about phasing in the deprecation in the product itself, maybe through developer tools or a variety of less aggressive or more aggressive warnings that are actually shown to users. And at a higher level, you might also wonder how to even choose among these various strategies and how to evaluate whether you made the right choice. So how do you know whether the deprecation strategy that you chose is resulting in the fastest ecosystem change and the least user pain and frustration? And this example of hypothetically deprecating TLS 1.2 is an example of what we call a security positive incompatible change, meaning a change that breaks existing websites in the name of security. And it happens pretty often on the web, and every time we roll out a change like this, we have to choose a strategy. Of course, it's not just for security. Breaking changes generally happen all the time on the web. They're not just for security reasons. But security-sensitive breaking changes have some special complications. So what's different about, for example, distrusting a CA or removing support for an old version of SSL than removing a CSS selector or deprecating some JavaScript storage API? What's so different about these security-sensitive breaking changes? Well, not always, but sometimes security-driven changes can be urgent. Even when they're not urgent, they're often time sensitive. So the longer we wait to make the change, the more risk users are exposed to. Secondly, security-driven incompatible changes aim to remove a risk, but if we're not careful about how we execute them, we could actually introduce risk as well. So for example, if a deprecation strategy involves a new warning, there's a risk of users becoming overwhelmed by warnings and starting to ignore all the security warnings that Chrome gives them. And this is a phenomenon that we call warning fatigue and that we really try to avoid. And finally, web users are often only as secure as the least secure browser available to them. What that means is that if we break something in Chrome in the name of security, it might just incentivize users to switch to a different browser where maybe the website works, but they're exposed to the exact same risk that we're trying to protect them from in Chrome. So we have to be really careful to roll out breaking changes in a way that explains what Chrome is protecting users from, and ideally in a way that doesn't drive them to just unknowingly accept the same risk in a different browser or platform. So today I'm going to tell you more about how we approach these highly sensitive deprecations. I found that breaking the web is really more of an art than a science, but whenever possible in Chrome, we try to approach it scientifically, and that's what I'm going to focus on today, are the ways in which we approach this problem scientifically. My hope is to shine a light on how your perhaps potentially disruptive security research might find a way into the real world. And I also want to highlight some open research questions in this area. So I'm going to start by describing the general process for incompatible changes in the Chromium project. And then I'll dive into some security relevant case studies that go through different steps in the process. So I'll start by giving, like I said, a brief overview of the process that the Chromium project uses to evaluate and approve breaking changes. And this is mostly not specific to security sensitive changes, but hopefully it'll give you an idea of what's involved. And I think you'll quickly notice that there's a lot of judgment and case by case evaluation in this process. And that's why it's sometimes so hard to know how to do it most effectively. The first step in any incompatible change is to assess the damage. And there are lots of different ways that you can do this, that you can measure breakage. Some of the metrics that we often use include the percent of affected page loads or connections, the number of affected sites, the percent of affected users, various other metrics too, depending on the deprecation in question. You could probably think of, another 10 examples of metrics that you could look at to measure any particular deprecation. So if you're proposing an incompatible change to the web as part of your research, you might wonder what you should aim for. And as a very rough rule of thumb, 0.001% of page loads is considered small breakage. So that's generally, in a target range for a deprecation. And at first glance, that sounds really quite small, 0.001%, but it still actually translates to a lot of real-world breakage. So you can see from this quote here, and this is even quite outdated, so these numbers are not exactly accurate, but it gives you a feeling for it. 0.0001% of page loads results in someone being frustrated every 3 seconds across the globe. So that's just a rough rule of thumb, but sometimes more bespoke measurements are required to make the case that breakage is acceptable. So here I'll give an example from the security domain, and that's the deprecation of what's known as mixed content. Mixed content is a term that we use when a secure HTTPS page loads insecure subresources like images. For a long time, browsers have blocked what we call active mixed content, and that's things like insecure scripts on secure pages. But mixed images, audio, and video have been allowed to load in most browsers for many years, and that creates the security and privacy risk of an attacker injecting content into these resources or eavesdropping on them. A couple of years ago, we decided to do something about this. And we embarked on a quest to remove mixed content entirely for websites rendered in Chrome. Since mixed content had been allowed for so long with really no sign of a deprecation in sight, it was pretty common at this point. It affected about 3% of page loads and about 4% of URLs in the HTTP archive in 2018. That's what we're showing here. And if you're not familiar, HTTP archive is this public data set of crawled web pages. So it was pretty prominent in this data set. And for this reason, we decided to auto-upgrade mixed content rather than just block it outright. And what I mean by that, auto-upgrade, is that Chrome now rewrites the URLs of mixed resources to HTTPS rather than just blocking them. So we automatically upgrade to HTTPS for mixed content, and if it doesn't work, then we block the resource load. And the hypothesis behind this strategy was that a significant amount of mixed content we speculated was due to developer error and could actually be fixed without the developer doing anything at all. So the speculation here is that the content was probably just available over HTTPS, and it was just a developer mistake to load the sub-resource with an HTTP URL instead of an HTTPS URL. And so we decided to try this auto-upgrading strategy. But it turned out this strategy introduced two measurement challenges that needed bespoke approaches. The first challenge is that we could no longer determine the breakage rate without actually causing the breakage. So in more detail, we knew how many page loads had mixed content on them, but we didn't know how many of those would auto upgrade successfully. And there was no way to get that number without just trying. So to get this measurement, we had to actually roll out a live experiment of auto upgrading to a small percentage of users. And this live experimentation strategy is somewhat unusual for deprecation in Chromium, but it worked in this case, and it allowed us to discover that indeed about half of mixed content could be transparently fixed via auto upgrading. The second challenge was that theoretically, this auto upgrading approach could have caused its own type of breakage. And the fear here, what I mean by this, is that if the browser is rewriting a sub-resource's URL to use HTTPS instead of HTTP, who's to say that this HTTPS sub-resource is actually the same resource as the HTTP version? Theoretically, there's no reason that the server has to provide the same resource over HTTP and HTTPS. And if they're different, we could cause some new exciting form of breakage, possibly even introduce a security risk. So this is an example of how a security-related breakage could actually introduce more risk. And initially, we weren't entirely comfortable saying that half of all mixed content could be auto-upgraded, when in fact, we didn't know if the auto-upgrade was actually resulting in the same resource. All we knew was that it returned an HTTP 200 response. So to measure this, we built a pipeline that consumes the HTTP archive, which is that public data set of crawled web pages I mentioned. And we analyzed all the mixed content in the HTTP archive and compared the HTTPS version of each mixed resource to the HTTP version. This involved some fuzzy hashing and image comparison algorithms to account for sort of small inconsequential variations. And with this comparison pipeline, we determined that about 99% of mixed resources are equivalent to their HTTPS versions, so that was a reassuring result. There was also a third challenge that we didn't really ever figure out how to address, and I think this is still an interesting open research problem. I suspect, but haven't been able to prove, that a good chunk of mixed content on the web is actually negligible from a user experience perspective. So think of things like tracking pixels and ads, or very minor visual elements, or UI controls that are very rarely used. These are things that, if they break, they don't really affect the user experience, but from the browser's perspective, a broken image is a broken image, and the browser can't really tell if the user cares about it or not. So this means that when we try to measure breakage via browser telemetry, we're really measuring an upper bound on breakage that matters. So I think it would be quite powerful to be able to measure at scale how much a particular incompatible change affects the user experience or not, but we don't really know how to do that yet. So for mixed content, it remains just an untested hypothesis. And in the hypothetical example of a TLS 1.2 deprecation that I gave earlier, this type of measurement would be quite interesting, because if we had to deprecate TLS 1.2, breakage would be really high, and so we'd want to get a tight estimate of breakage, and an upper bound might not really cut it. So important open research problem that I would love to see solved. All right, so as I've discussed with the mixed content example, the very first step in the deprecation process, measuring the breakage, can be quite involved. Once that's done, after assessing the damage, the next step in shipping an incompatible change is to get approval from the powers that be. So this step of shipping an incompatible change after you have your assessment of the damage, your measurement of the breakage, this step is sending what's called an intent to remove to a public Chromium mailing list. And this email follows a template that assesses many aspects of the change, such as how much burden it places on developers, how severe the breakage is from a user perspective, how the change affects the user experience, whether other browsers are following suit, implementing the change, whether it's standardized, and more dimensions like that. And all this data gets reviewed and needs approval by 3 senior project members. And this is where a lot of the art and the judgment calls come in. So for example, an urgent security change will often have a higher acceptable breakage rate than a small aesthetic change. So there's really no one-size-fits-all threshold for all breaking changes. At this point, once the change is approved, the process can look very different for different changes. At the very least, there's usually a message in the developer tools console for a couple releases before the incompatible change is actually landed. You can see an example of that for mixed content here. But there can also be months of intensive outreach campaigns, opt-in or opt-out phases, and many other possible elaborate deprecation strategies, depending on how severe the breakage is. And in the rest of the talk, I'll get into more detail about how we can evaluate and experimentally compare these strategies. Ultimately, even though, as I've described, there is a well-oiled and well-exercised process for shipping incompatible changes in Chromium, there's a lot of latitude in how each change is executed, and that's why I call it more of an art than a science. So personally, when I read research papers that propose incompatible changes, I find them most compelling when they consider all of these aspects of a breaking change that we consider as part of this process. And also, on the other side of the coin, I want to emphasize that there is this very commonly used process, even if it involves some judgment calls. So my message to you as researchers is that you don't need to shy away from proposing breaking changes if they are realistic and evaluated well. So this is an overview of the deprecation process, but I haven't talked yet much about the science of choosing a deprecation strategy. And as I mentioned at the beginning of this talk, security-motivated breaking changes are often time-sensitive and complex. So for security changes in particular, it's pretty crucial to move the ecosystem quickly but delicately. And we often find ourselves looking at breakage that's higher than the typically allowable deprecation thresholds. We're sometimes looking at maybe 0.3% of page loads instead of 0.0001%. So next I'll talk about work that we've done to try to experimentally narrow down the many options for how to pull off a deprecation, both in the outreach phase and then in the implementation phase. So let's return to our hypothetical example where you're working on a browser security team and you are trying to drive down TLS 1.2 usage as much as possible so that you can deprecate it as quickly as possible. And let's suppose that outreach to affected server operators is part of the deprecation strategy that you've chosen. So in one way or another, you want to contact these affected server operators to let them know that they need to move to TLS 1.3. At first glance, outreach might not really seem like something you can run experiments with. And that's more or less true for broad outreach, at least as far as I can see. You can't really publish a blog post and then have one group of server operators see the blog post and another not see it, and see which group remediates the issue faster. That's just not really how blog posts work. You could maybe do some qualitative work. For example, something like surveying server operators about what influenced their decision to remediate or not remediate, but it would be pretty hard to get an unbiased data set there. It wouldn't really be a controlled experiment. But targeted outreach is a different story. And in fact, there's a decent sized body of work, which many of you may already be familiar with, researching how direct notifications influence server operators to take action on a pretty broad range of security issues. And much of this research looks at not just whether notifications are effective, but also tests different variations on notifications to see whether things like different language choices or different presentations of the issue are more or less effective. My team ran our own experiment of this nature to test whether direct notifications can influence server operators to fix HTTPS misconfigurations, so things like expired certificates or outdated protocol versions. So we crawled the web to discover many millions of sites with HTTPS-related misconfigurations. They're very common, and we divided them into various experiment groups where we were testing different types of notifications. And so, for example, one of the main variables that we were looking at was the channel of the notification. One channel being Google's Search Console product. Search Console is a tool that website owners can register for to receive insights about how Google is crawling their sites. And that includes direct emails from Search Console about discoveries like security issues. And the other channel that we tested was a direct email to an email address that we discovered via Whois lookup. The results looked something like this. And when you're reading these graphs, it's showing the percentage of sites that have the given misconfiguration over time. So going down and to the right fastest is what we're looking for. Down and to the right is better. The solid blue line is the Search Console treatment, and the dashed green line is the Whois treatment, and the other two lines are the controls. So overall, notifications appear to help for at least some misconfiguration types, but the effect is mostly pretty small, and we didn't detect any differences among the different message variations that we tested. So there was some evidence that the Search Console notifications were more effective than Whois notifications, but this evidence was somewhat mixed. And finally, we found that simply being registered with Search Console makes a site more likely to remediate when it receives a notification, even if that notification isn't actually coming from Search Console. So we had to kind of account for this population difference in all the tests that we did. As a sort of bonus case study, our experiment with these notifications happened to overlap with a major CA distrust event. So this was an event where Chrome distrusted the Symantec PKI, and sites that used Symantec certificates had to replace their certificates. And we could draw an interesting contrast between this distrust event and the HTTPS misconfigurations that we were studying with these notifications I just described. The contrast is this. In the Symantec distrust, the breakage was going to happen. We had set a date for distrust. It was going to cause a bunch of sites to show big, scary certificate errors, and now it was a matter of getting as many affected sites as possible to fix. Whereas with the other HTTPS misconfigurations that we had been sending notifications about, there was no timeline for actually removing support for most of these configurations. So we wanted to get site owners to fix them, but there was no firm plan for anything bad to happen if they didn't. So we conducted A similar, though somewhat simplified experiment where we notified sites that were affected by the semantic distrust via Search Console. And here, in this case, we didn't detect any significant effect of the notifications. Though, we also, you can see here that the absolute remediation rates were much higher than the other types of misconfigurations that we studied. And so our theory here is that in an event like the semantic distrust, where there's a lot of publicity and broad outreach, and the threat of breakage is pretty imminent. So site owners are highly incentivized to act. In a scenario like this, the effect of direct notifications seems to be pretty much completely diluted by these other dynamics at play. One observation from this work is that our results are somewhat at odds with the existing body of security notifications research. Um, what I mean is that other research found much more pronounced effects from remediation. For example, a study of email notifications about the Heartbleed vulnerability saw an increase in patch rates of 47%, which was a much bigger effect than we saw. And what's going on here? I don't know exactly. One possibility is that notifications for different types of issues really elicit very different behaviors. Another possibility is that null or small results aren't getting published, so the body of published work makes it look like security notifications are more effective than they actually are. Personally, my takeaway that I apply to my own work is that direct targeted outreach isn't a surefire standalone strategy. So if you find yourself pondering whether an incompatible change is realistic, you may want to consider what other than targeted outreach might be able to motivate site owners to act. And as this research area matures, I think it might become a fruitful target for some systematization of knowledge, or a meta study. Maybe patterns emerge. For example, maybe the more direct security impact there is to users, the more effective direct notifications to server operators. So personally, I would love to read an SOK on this as it matures. All right, so I began this talk by this thought exercise where I told you to imagine that your task is to get as many server operators as possible to move to TLS 1.3. And then eventually, you want to remove support for TLS 1.2 from the hypothetical browser that you are working on the security team for. And there's actually a sub-question hidden in there. What does it even mean to remove support for some particular configuration? There's really a spectrum of options here, from simply removing support, just like ripping out the code that supports the feature and showing some kind of generic error, to maybe towards the other end of the spectrum, you could think about showing any number of a softer set of warnings which the user can choose to ignore and accept the risk. So here are some very concrete examples of points on that spectrum for HTTPS-related misconfigurations. So for some on the more aggressive end of the spectrum, for some very ancient, very insecure TLS configurations, Chrome just treats it as an error, as if the name didn't resolve or the server refused the connection. The resource load just fails and there's nothing the user can do about it. Closer towards the middle of the spectrum, for some other types of HTTPS problems, such as an invalid certificate, Chrome shows a bypassable warning. So this warning is designed to make it non-obvious how to bypass, but a determined user can do so by finding this subtle circled link here. And for even more common security problems, such as a website that doesn't use HTTPS at all, on the way less aggressive end of the spectrum, Chrome shows a warning in the address bar. but it doesn't intervene with, it doesn't stop the user from using the page. And there are also various other UI options that we use in different circumstances, such as popover warnings, info bars, less scary warning pages. So these things I've shown here are just some examples of points on the spectrum, and there are many others. Ideally, really from a security perspective, any non-ideal security configuration would be a hard fail error, non-bypassable, just can't load that page. But there is a complex set of factors that informs how we choose any one of these UIs for any particular breaking change. And the factors include the risk that the user faces, how often and on what types of sites the UI will appear, how complex the risk is to explain, how quickly the UI will get server operators to remediate the issue, and many more. So very complex decision space here. Now, in the TLS 1.2 hypothetical example that I gave, we'd be facing an issue that users encounter quite commonly because TLS 1.2 is very widespread on the web today. So a hard fail error, this most aggressive point on the spectrum, would probably be a no-go, and we'd want to pick somewhere else on the warning spectrum. These kinds of cases are very interesting and challenging because they have a very complex optimization function. The stronger the warning, the more we run the risk of creating warning fatigue, which is when users see warnings everywhere and therefore start to ignore them. But on the other hand, the weaker the warning is, the slower sites might remediate. And we suspect that sites that are experiencing a full non-bypassable warning are going to remediate faster than sites with a more subtle warning. Users or server operators might not even notice the more subtle warning. So somewhere in here, we hope there might be a happy medium, some kind of UI that, in our hypothetical, would encourage server operators to move to TLS 1.3 while informing users of the risks of TLS 1.2, but not annoying or scaring or confusing them too much. So that's kind of the ideal happy medium that we might hope exists somewhere in here. And we somewhat recently wanted to actually try to somewhat scientifically figure out what this happy medium is. And this was actually for a somewhat similar scenario as the hypothetical I gave you. In real life, not hypothetically, we decided to deprecate TLS 1.0 and 1.1, so older versions of TLS. All major browser vendors announced this in coordination in 2018, that these older versions of TLS would be deprecated. But at the time of that announcement, their usage was still quite high. It was something like 0.5% of all connections in Chrome. So, where I said before 0.0001% is considered quite small breakage, 0.5% is considered quite high. So we knew we had to take some deprecation strategy to try to drive down usage before removing support entirely. And we decided to use this as an opportunity to experiment and to try to gain some insight into how different warning UIs in the product might influence server operators to migrate to a newer version of TLS. And, so in other words, we were trying to measure how much faster can different warning UI cause sites to remediate, how much less warning fatigue do they create. And this experiment was a bit unusual. Chrome has a robust experimentation framework, but it's set up and designed for running A/B tests to measure how Chrome product changes influence user behavior. But in this case, in this experiment, we want to measure how Chrome product changes influence server operator behavior. So in other words, does a full page warning, for example, get sites to migrate to newer versions of TLS faster than a more subtle warning? And how much faster? if so. So we built some custom infrastructure for this experiment because, as I said, this is not really what Chrome's experimentation framework is set up for. So we crawled the web for sites that needed to migrate off of TLS 1.0 and 1.1 to a newer version. And as in the notifications experiment that I mentioned earlier, we divided these sites into experiment groups. Then we shipped these groupings to Chrome. So Chrome actually varied the warning UI for different sites, depending on whether they were in the control or treatment groups. And we ran the experiment in 2 subsequent phases. In the first phase, we showed this subtle omnibox warning, which is similar to what we show for sites that aren't using HTTPS at all. So sites in the treatment group got this warning. Sites in the control group did not. They were treated just as regular HTTPS sites with no security problems. And in the second phase, we used as our treatment a bypassable warning page, though it was less severe than the warning page that we use for an invalid certificate, for example. So designed to be less scary than that. And then we measured how quickly sites adopted modern TLS versions for sites in the treatment group that had these warning UIs versus sites in the control group, which didn't have any warning UI at all. And this is an overview of the results. These graphs, sorry for flipping this on you, but these graphs are showing percentage sites that have remediated over time. So in these graphs, up and to the right, faster is better. You can see here that as expected, the full page warning UI in phase 2 caused significantly faster remediation than the more subtle warning in phase 1. This was still a marginally significant effect in phase 1 for encouraging remediation, but it was significantly less pronounced than phase 2. Another interesting thing is that overall, even in the control group, remediation was way higher in phase 2 than phase 1, even in the control group. And we don't know for sure why this is, why the baseline was so much higher, but some theories might be that there was greater public awareness of this change at this point by the time we got to phase 2. Or could also be that the control sites benefited from the warning treatment indirectly. For example, if they were hosted by a shared hosting provider that learned about the warning UI and upgraded the TLS version for all of its customers at once. Another quick thing I'll note here is that in phase 1, with the more subtle warning UI, we didn't see much change in a suite of user behavior metrics that we looked at. So things like navigations to affected pages or downloads or form submissions on affected pages, things like that. We didn't see much movement in those metrics when this warning was shown in the address bar. And we consider that a good thing because it shows us that the subtle warning UI is doing what it's intended to do. It's kind of subtly nudging websites to migrate without overly scaring or confusing users. So in this case, not seeing changes in these user behavior metrics was a good thing. Now, this TLS 1.0 and 1.1 deprecation isn't exactly the same as the TLS 1.2 hypothetical scenario that I posed as a challenge. 1.2 would be in much higher usage if we needed to deprecate it tomorrow. So we might not be able to exactly apply the results of one to another. Every security-related breaking change has its own unique challenges and circumstances. So, again, it's an art, not a science. But I think that by running experiments like this, we do start to build up some fairly well-grounded intuition about what works and how well it works. So to conclude my talk today, I want to zoom out a bit. I've talked a lot about the particulars of the measurement and deprecation process and given you some look at the experiments that we've run to make decisions about how to roll out a breaking change, things like whether it should be done quickly or gradually, how user-facing browser UI makes its way to into motivating site owners, how to reach site owners directly through targeted outreach. But those are all kind of details. And if there are two things that I want you to take away from this talk, it's this. First of all, it's that incompatible changes get deployed all the time on the web platform. And there's a process and lots of prior art how to deploy changes like this, especially when it comes to security-related changes. Anyone, any member of the public can propose and implement breaking changes in the Chromium project, as long as they measure the breakage carefully and they make a case for why it's acceptable, and they evaluate some of the various axes I talked about, like developer impact and standardization. So when I'm reading a research paper that aims for real world impact, I would almost rather read a paper that proposes a careful and realistic deprecation strategy rather than a paper that introduces a lot of complexity to avoid any amount of incompatibility. In other words, a thoughtful incompatibility is probably a lot more shippable than a complex compatibility hack, especially if there's a delta in security properties and we're sort of like taking a security hit for the compatibility hack. The second thing I want to take away is that the deprecation process itself can be studied empirically. And my experience is it's actually a fruitful research area. At first glance, I find that the details of a deprecation look kind of like a product strategy question where you just have to make informed decisions as best you can and try to incorporate the results into your experience as you go forward. But I find when I look a little bit closer, some details of deprecation strategies can actually be tested experimentally. And because of work that we've done in this area with security-related deprecations, I feel like we now know much better how, for example, how much to rely on targeted developer outreach as well as different browser UI treatments for moving the ecosystem. So it is possible to learn things scientifically here if you look closely and think about it carefully. I hope that this talk has given you some insight into how incompatible changes are deployed on the web and how we can think about them as a research area, especially with all the exciting complexities that are introduced when the change is security related. So to return to the thought exercise I posed at the beginning of this talk, my hope is that if you found yourself in the position of deprecating TLS 1.2 on the web tomorrow, you'd now have an idea of how to go about doing that, or at least have some ideas for interesting experiments to run in the process. So thanks very much for listening, and I'm looking forward to your questions.